lectures. Yeah, so we had a function f from a bounded interval ab to r. The fundamental assumption is that this function is bounded. This was our assumption, fine. And then for a partition P of AB, we defined what is known as UPF, the upper sum corresponding to the partition P and the function f. And similarly, we also define what is known as LPF, the lower sum. Now, upper sums, they decrease with respect to the refinements, while lower sums, they increase with respect to refinements. And therefore, we defined what are known as upper integral and lower integral. Yes, so these two are defined. And then we said that a function is Riemann integrable if and only if upper integral and lower integral, they are one and the same. Right. And then we had some examples. We saw some functions which are integrable and a function which is not integrable. Fine. And then we had a characterization. Yeah, so f is Riemann integrable if and only if for every epsilon greater than 0, there exists a partition P epsilon such that upper sum minus the lower sum is less than epsilon. Right. Yeah, so this we saw. So what was the last one that we did? Did we look at any example? Did we look at any example?
No, sir.
No, sir.
So this was the last one that we did, or we did something else?
Sir, this was the last thing.
Last.
Okay, fine. Okay, yeah. Maybe we will have a large class of examples given by the following corollary. Yes. Yeah. So let f from AB to R be a continuous function. Then f is Riemann integrable. Yes. Yeah. So one thing that you'll have to note that I haven't assumed that the function is not I haven't assumed that it is bounded. Is it necessary? So should I assume that the function is a bounded continuous function? Rather than
No,
The
sir.
continuous with a closed interval, so boundedness is implied.
Exactly right. Right. So our aim is to make use of this characterization. So this is the characterization that we are interested in. So we wanted to make use of this. So let's start with an epsilon positive. Right. So start with an epsilon positive. Now I have a continuous function, and therefore since f is continuous, there exists delta greater than 0 such that mod fx minus fy is less than epsilon whenever mod x minus y is less than delta. Right. Fine. Now, I wanted a partition. So, what will be the choice of the partition? What will be the choice of the partition? Any guess?
B minus A by N up to.
What is n? How will you choose your n?
Such that every partition is smaller than epsilon.
Every partition?
Every like b minus a by n is smaller than epsilon for every like all the
Epsilon.
Delta.
all
Epsilon.
the
Sir,
subintervals
delta.
are smaller than
Delta.
L. Oh yes.
Every partition shall be less than delta.
Choose any partition such that the maximum width that you can expect is less than delta. So choose a partition P of the interval AB such that the maximum one less than so what is the partition? The partition that I wanted is x0, x1. Now let me say it is up to xn. Yeah, so this is the partition. Of course, x0 is a and xn is b. 1 less than or equal to k less than or equal to n. Mod xk minus, well, I don't need this mod. Xk minus 1. Yeah. So this maximum should be less than delta. I choose one partition of this form. That much is enough. Yes. And then next one. For each 1 less than or equal to k less than or equal to n, there exists yk comma yk dash in the interval xk minus 1 to xk such that yes, f at yk is equal to infimum over t in the interval xk minus 1 to xk f of t, and f at yk dash will be supremum over t in the interval xk minus 1 to xk f of t. Yeah, so how do we know the existence of such points? How do we know that such points exist?
Sir, because these subintervals are compact and f is a continuous function, so it will attain its bounds.
Yes. So you have a continuous function and it's a closed and bounded interval. Therefore, it attains the maximum and minimum. Right? The infimum and supremum are actually attained. So such points exist. Because f is continuous. Right. And that's it, done. Now we will have to calculate UPF minus LPF. Yeah, so which by definition is summation k running from 1 to n. Yeah, this is mk into xk minus 1 minus summation k running from 1 to n small mi into xk minus 1, which is same as summation k running from 1 to n. So I can club these two, and mk is exactly f at yk dash, capital Mk. So this is f at yk dash, and small mi is f at yk times xk minus 1. Yes. And yk minus 1, they all come from this interval xk minus 1 xk, and the distance is less than delta, and therefore because it is less than delta, by continuity we have first one, that it is going to be less than epsilon. So less than epsilon times summation k running from 1 to n xk minus 1. Yeah. And you can notice that all the terms gets cancelled in the summation except the first a and the last b, and therefore this is only epsilon into b minus a. Yeah, so what we are going to do is that to avoid this b minus a, here divide by b minus a, so that you will have it as by b minus a upon b minus a, which will give you epsilon. That's it. Right? Yes. Yes, the next corollary. So yeah, I'll I wanted to do one example. Well, let me do one example and then we should be able to proceed further. Example. Yeah, we have already seen a large class of functions known as the continuous functions. They all are Riemann integrable, right? Which means the next one is a discontinuous function. Consider the function f from 0, 1 to r given by fx equal to 1 fx not equal to half, 0 at x equal to half. Right. Yeah. Yes, so first thing that can be observed that, well, I'll simply write it as it is clear that one doesn't have to. For any partition, you choose any partition, for any partition P of the interval 0, 1, what will be the lower sum? Sorry, upper sum. That's what I wanted. What will be the upper sum? What is the upper sum?
1 by 2. 1 by 2.
1 by 2. How did you get it as 1 by 2?
1. 1. 1.
1, sir.
1, sir. 1, 1.
1. Right. Right. Now, I wanted to use the characterization. So, let epsilon greater than 0. Yes. So, now, can you guess the partition that does the job? Just get me the partition. In this case, it is quite easy.
Sir, 1 by 2 will be a point of that partition.
1 by 2?
Will be a point of that partition. Any partition containing 1 by 2.
Any partition containing 1 by 2?
Yes.
Can you be...
So maybe we can take 0 to half minus epsilon by 2, then half plus half minus epsilon by 2, half plus epsilon by 2, and 10 to 1.
So now consider the partition. P epsilon, this is what we wanted. 0, half minus epsilon by 2, half plus epsilon by 2, and then 1. Yes. For this partition. Now, so we know already what is UP epsilon. So what is LP epsilon F? Yes, start. Calculate and then tell me.
Sir,
Huh.
sir, can you please tell me how the upper sum is 1?
The function is 1 throughout, except the point half. You
Sir,
choose
the
well.
function.
Well.
Acha, okay. Sorry.
Yes, what is LP epsilon F?
1 minus epsilon.
Epsilon.
Louder.
1 minus epsilon.
That's it, done. 1 minus epsilon. So I'll simply say verify. I'm not going to verify it. Right. So now you have this, and therefore, well, if you want maybe for calculation purpose, well, you could have even chosen, if you are very specific about less than epsilon, then choose it as epsilon by 4, so that you will get it as 1 minus epsilon by 2, and therefore UP epsilon F minus LP epsilon F, which is going to be just epsilon by 2, which is less than epsilon. If you are very specific about less than epsilon, then fine. Otherwise, you could have even epsilon by 2 works, but still. Right. Yeah. So now, instead of doing it for an arbitrary epsilon, so let's do it for epsilon as 1 by n. So if you do that, then you get the following. What is that? Bounded function f from AB to R is Riemann integrable if and only if there exists a sequence Pn of partitions such that limit n tending to infinity UPNF minus LPNF. Yes, so this limit should be 0. Yes. Yeah. So It's a direct consequence of what we have done. So once you know that it is Riemann integrable, then you get a sequence of partitions, right? So once you know that it is Riemann integrable, then for each epsilon you get a partition, and therefore you choose for each 1 by n you choose a partition such that UPNF minus LPNF is less than 1 by n, and this sequence should help you. And on the other hand, if you have a sequence with this property, then choose n naught such that 1 by n naught is less than epsilon, and that should help you. Or so choose epsilon, so choose n naught such that UPNF minus LPNF is less than epsilon for all n bigger than or equal to n naught, and that should help you. So I'm not going to do this. Easy corollary.
So please explain again.
Yeah, so I don't have to explain more. That's the main point. Give a try. Just give a try, then you should be able to. Just use the previous characterization, then you should be. That's the whole point that I wanted to insist. Yes.
Sir,
so
in
I'm just
previous
leaving it as an exercise. Yes.
Sir, how we get that partition, sir? What is the institution behind that partition?
Which partition?
1 by 2 minus epsilon by 4, that.
So somehow or the other, see, the problem is only at 0. Sorry, half. The problem is only at half. Right? So somehow or the other, wherever there is a discontinuity, come up with a small interval. That's the whole idea. Make the interval as small as possible. That's exactly what I have done.
Okay, sir.
सर 1 की जगह पे वो LP एप्सिलॉन एफ लिखेंगे
कहाँ पे?
करोलरी के ऊपर।
करोलरी के ऊपर
1 की जगह पे आपने LP एप्सिलॉन एफ लिखा है।
1 की जगह पे कहाँ?
सर वेरीफाई जहाँ पे लिखा है।
वेरीफाई लिखा है, LP एप्सिलॉन F इक्वल टू 1 माइनस एप्सिलॉन बाई 2 लिखा है, उसके बगल में वेरीफाई लिखा है। ठीक है, मतलब वेरीफाई इट, मेक श्योर दैट इट इज एक्चुअली दैट यू गेट दिस वैल्यू, यही चाहिए मुझे। अगर किसी ने अभी तक वेरीफाई किया नहीं तब प्लीज वेरीफाई इट। Yes. Yeah, so now well, see, these are not the original ideas of Riemann. That we should understand. The original ideas of Riemann, so I just wanted to see what they are, give a flavor of that, and then we'll see something else, and then we'll stop. Riemann integration, because our aim is not to do more on Riemann integration. Yeah, by next lecture we should be able to stop this or finish this Riemann integration. Let P equal to, you choose a partition, be a partition, be a partition of the interval AB, and let T equal to capital T, although psi I, such that 1 less than or equal to I less than or equal to n. Well, what are these? With psi I coming from the interval xi minus 1 comma xi for all 1 less than or equal to I less than or equal to n. Yes. Yes, so this set T, the set T is called as the tag set. For the partition P, corresponding to the partition you have chosen. This is only each one's choice. And then given f from AB to R, the sum, so let me, so corresponding to the, so this is corresponding to the partition, tag set, and then the function. So this is defined as summation k running from 1 to n f at psi I xi minus 1. This sum is called as the Riemann sum or Darboux sum. Right. So this is the Darboux sum of f with respect to the partition P and the tag set T. Fine. And then the quantity, what is that? So let me define what is known as mod P. This is which is maximum.
Sir, for summation you are taking variable from k equal to 1 to n. Inside the summation you are taking the suffix I. Is both thing different?
Thank you. Right. Right. So this is what is called as the mesh of the partition. Right, this is what is known as the mesh of this partition. Right. So well, one easy thing that you can always observe is that LPF is smaller than the Riemann sum which is less than or equal to the upper sum. Right. So this you can easily observe. Yes. For any given partition, P and a tag set, this you can easily observe. Yes. So now an easy corollary. So if the function is Riemann integrable, what will happen to the where will the supremum of the lower sums go to?
Sir, lower integral.
Lower integral. When the function is Riemann integrable.
Sir, upper integral.
I mean integral a to b f, right?
Yes, sir.
And if it is, and the upper sums, they go to
integral a to b f.
And therefore the in between one, it should also
by a squeeze principle.
Right. So let f from AB to R be Riemann integrable. Then for any epsilon positive, there exists so there exists delta greater than 0. I think there is some internet issue. Just give me a second. Just give me 1 second. Right. Yes. So if you have a Riemann integrable function, then for any epsilon positive, there exists delta greater than 0 such that for any partition with the mesh of the partition being less than delta, such that the difference between the Riemann sum and the value of the integral, this can be made less than epsilon for any tag set T. Right. Yeah, so this follows from the fact that the function is Riemann integrable because upper sum and lower sum, they both converge towards the integral and therefore you get this. That's the whole idea. Fine. Corollary, the next one. If f from AB to R is Riemann integrable, then for any sequence Pn of partitions with the mesh tending to 0, we have limit n tending to infinity UPNF equal to limit n tending to infinity LPNF equal to integral a to b f. Yes. In fact, this is also going to coincide with the limit of the corresponding Riemann sums. That's the whole point, because for each partition you can choose a tag set and then from there you can again, that is again also going to happen. So I haven't written, but still. Right. Yeah. So with all these things, because it is not the so sometimes to calculate the value of the Riemann integration or integral, you may not be even able to find you can somehow or the other show that it is Riemann integrable, but how to find the value, it is these partitions that are going to help us. That's the whole point. Right. Now let's look at some more examples. Yes, so what you do is you consider the function. Maybe I'll simply put it as example. Right. You consider the function f from 0, 1 to r given by fx equal to 1, fx equal to 1 by n, 0 otherwise. Right. Yes. Okay, so now for any partition, what is the lower sum? What will be the lower sum?
0.
0, sir.
0, right. Yeah, so notice that for any partition, P LPF is 0. Yes. Fine. Now, what we wanted is other points. Yes. So how to go about other points? Well, what we wanted is the upper sum, right? So how to get the upper sum?
We can take sequence of partitions.
Yes. So how do you choose your sequence of partitions?
Like first will 0 to 1, then second 0, half 1, then 0, 1 by 3, half 1.
Will that help you? Will that help you?
Sir, if we keep on doing this thing, we get only a finite number of 1 by n. So if we keep on refining, then we get like more and more number of points which are in the form 1 by n. Then consequently we get the question.
Well, somehow we need to use the characterization. So because if we know that the function is Riemann integrable, then you can use this. But we do not know whether it is Riemann integrable or not. That part we'll have to take care. So let epsilon greater than 0, right? And then choose n epsilon, because this n depends on epsilon, therefore I'm writing it. And n such that one by n epsilon is less than n. Sorry, is less than epsilon. How do you know that such an n epsilon or such a natural number exists?
Sir,
Sir,
by
by
Archimedean
Archimedean
property.
property.
Archimedean property. Such a number exists by Archimedean property. Right. By Archimedean property. Fine. Then what you do? Yes. What will be your choice of the partition? So now what you do is that here so let P epsilon equal to 0, 1 by n epsilon, and then starting from 1 by epsilon, how many points of discontinuity do we have?
Countable infinite.
Sir, n epsilon points.
Right. Right. So up to 1. So my question is from 1 by n epsilon to 1. So you have n epsilon points. Right. So 1 by, what should I write? There it was only 1. Therefore we chose the points as half minus epsilon by 4 and half plus epsilon by 4. So we will have to, yes, so how are we going to do this? 1 by n epsilon plus epsilon upon 2 or 4. 2 times, I think it's n epsilon. Then we'll correct it.
N epsilon.
Huh?
Sir, 2 to the n epsilon.
2n, not 2 to 2 raised to the power 2n epsilon. And then 1 by n epsilon minus 1. Minus 1 minus epsilon upon 2n epsilon 1 by n epsilon minus 1 plus epsilon upon 2n epsilon up to I will have it as 1 by 2 minus epsilon upon 2n epsilon 1 by 2 plus epsilon upon 2n epsilon 1 minus epsilon upon 2n epsilon and then 1. Yes. Yeah. Now, so exercises. Calculate UP epsilon. Yes. So calculate this and then find the difference. Or simply, I'll simply say finish this example. Right. This is the first exercise, and the second exercise that I would like to give here is that,
So the partition we have chose, we are using epsilon upon 2 and epsilon. Sir, it is equivalent to saying that it is less than epsilon square by 2. So, sir, the difference is either less than equals to epsilon square by 2. We cannot ensure it is less than epsilon.
Why? Why it is not less than epsilon? Epsilon square is less than epsilon because epsilon is something which is less than 1.
Oh, okay. Thank you, sir.
Our interest is not on epsilon being large. That is the whole idea. Not that you choose epsilon as 10 or 20 or 1000. Our interest is only on smaller epsilons. Okay, so yeah, so by all these examples, I know you should be confirmed, you should be convinced why this exercise is true. Let f from AB to R be a bounded function. Function having only having the at most finitely many why having blah 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 be a bounded function with at most finitely many discontinuities. Why at most? With finitely many discontinuities. Show that f is Riemann integrable. Right. Yeah, this is not a difficult exercise. This you should be able to. Yeah. So I think the time is up. And with this, let me stop today's one. If you have any questions, you are most welcome to ask.